Physics 3030, the universe. This is lecture 7. And this lecture is going to be about the early universe. This is the universe before recombination, before the microwave background gets sent away. And we will begin this lecture by talking about particle accelerators, and then we'll talk about the early universe, and then we'll talk a little bit about the unification of forces, which is talked about in this section of your book. Okay, so we're going to talk first about particle accelerators. And the interesting thing about particle accelerators is that you really can think of them as laboratory experiments concerning the early universe. And particle accelerators, obviously, hopefully the name implies that you accelerate particles to huge speeds, and you do that by using a changing electric field, or electric field and magnetic field, okay, to pull particles around, okay? And there are different names and different types of particle accelerators. A cyclotron is only an electric field. Okay, a synchrotron is both an electric field and a magnetic field. And there are other different types of particle accelerators. And I don't want to talk too much about the details of how those exactly work. But the idea about these is that you use high energy particles to probe smaller and smaller structures. And the reason for this, there's an equation from quantum mechanics, okay, that says that this is the de Broglie wavelength, that there is sort of the de Broglie wavelength. This is the wavelength of a particle, okay, which doesn't make much sense. When I really think about it, this has to do with particle-wave duality from quantum mechanics. But the idea here is that looking at this equation, okay, this is the gist of what I want to say is the energy is on the top over here, the wavelength is on the bottom down here. So as the energy goes up, the wavelength goes down, and small wavelength allows you to look at small things, because the length of the wavelength is what I can probe and what I can look at. Okay. And there are two main ways that we look at particles. So I can shoot particles at other particles this is way one, at other particles, and watch how they bounce off. Okay, and this gives us some kind of scattering idea. So you have some particle, you have some other particle that goes off of it and gets shot off, and some of them scatter that way, some of them bounce back, and you put a detector, right, a detector around these guys, and the angles, the different angles that you can measure tell you about what's going on in this really, really small scale here. Okay, that's one way in which we do this. The other way, which is sort of way more fun and a neat way to think about them, is that you can shoot them at each other Okay, and it actually doesn't matter whether one is stationary or both are stationary. You're shooting them both at each other, but if you shoot them both at each other, you can get much higher energy. So with enormous energy, okay, and when you do that, you produce, let's put it down here, produce new particles. Okay, so you throw two protons together and you just get this giant shower. So what ends up happening is, let's draw a little box over here. So in the first case, maybe I'll shoot one particle this way and one particle this way. And when they hit each other, whatever comes off, you get all kinds of stuff in all different directions, right? All different kinds of particles. And the idea is that in the first case, you don't really have enough energy to do this. In the second case, there's so much energy in these particles that the energy, again, because of E equals mc squared, the energy of the particles gets turned to even more mass, and it creates all of these guys. Okay, and this is how we've made a lot of the new particles we see, and a lot of these are unstable. They then decay really quickly. We have to have detectors right around where these things are pummeling into each other to see what's going on. And this is what they're trying to do to make the Higgs boson. They're throwing large hadrons at each other and colliding them. And the collider means there's two different beams of protons getting shot at each other. Okay. Now again, the difference between 1 and 2 is not so much whether one's stationary and one's not stationary. It's just the energy. Okay. So this is sort of the first one is sort of a medium energy, right? And this is a really high energy. Okay. And what do we mean by really high and really big and really small? Well, the way that we measure energy at these small scales has to do with the way that we measure energy at these small scales has to do with the units that we use, is called the electron volt. And what it really is it's units where it's the charge of the electron. So this is sort of the charge. This is what you're seeing in your book all over the place. Charge of the electron times 1 volt, which is the unit that we use to measure an electric field. Well, it turns out if you look at the units of these two together, so this is actually equal to a unit of energy. So an electron volt, this is what we use to, volt is what we measure an electric field with. Okay, and it's basically the energy of 1 electron in a 1 volt electric field. Okay, and that might seem abstract, but it's really useful for particle physicists because it's just one of the things you're dealing with all the time is these electrons. Okay, and we're going to talk about energies a lot, and these energies are actually measured in. So we'll throw different prefixes in front of this. So it's usually written little e times big V, right? And then you might see a mega electron volt, which is million, giga electron volt, tera electron volt. So this is getting bigger and bigger, right? And there could be a kilo electron volt in between those two. Okay, that's million, that's billion, that's trillion. Okay, so we're going to start talking about these things. And let's talk about some famous particle accelerators. Okay, so there's sort of list of particle accelerators. There's the Stanford Linear Accelerator called SLAC. Okay, this is just some examples, just so you have. There's one in Fermilab, which is in Illinois, and it's called the Tevatron. It's called the Tevatron because it was one of the first one of the first accelerators to break the TeV barrier. Okay, so that's a trillion electron volts, and when a lot of times this is the energy. This is what we're really referred to of a single particle, right? If I use the Google box to calculate what one electron volt is in joules, which is what we normally measure energy in, then it would be tiny, tiny, tiny. But for one particle to have that amount of energy is a different story, right? It's getting all of that energy into one particle. So when I go up to a TeV, even then, if I measured how many joules that would be, it wouldn't even be 1 joule. But for one particle to have that much energy, that's a big deal. Okay, and then we'll talk about, and then the other one that I wanted to write up here is the Large Hadron Collider at CERN, which is a conglomeration of European folks doing research, and there's actually a lot of American money in CERN as well, and it's in Switzerland, or on the border of Switzerland. Okay, and the Large Hadron Collider is multiple TeV. I think they got up to 4 TeV last year. They can go up to like 12 or 16 or something like that. Very, very big. And this one was built for the Higgs boson. Okay, and let's show you guys some pictures of those. So this is a picture of part of the Large Hadron Collider. I really like this picture. This is just the detector. So this is before they finish building it, and the idea is there's going to be some tube here, okay, a vacuum tube. Why a vacuum tube? Because if there was air in here, the particles, the protons, would hit the air molecules, and you wouldn't get much. So you get them moving here, and you get protons coming from this end, you get protons coming from this end, and you make them collide right here. And when they collide, they shoot off all kinds of new particles in all kinds of different directions inside this detector. And you can see this detector looks really complicated, and there's billions and billions of fiber optic cables coming into this thing, okay? And there's all kinds of engineering that needs to go into doing this. This is the largest collider that's ever been built. It's the largest experiment ever done by humans, okay? And we are probing the universe with these things. And this is really getting up to energies that are close to parts of the Big Bang. Now, we're going to start talking about that here in a second, but you'll see that the energy of the Big Bang is much bigger right at the beginning, but then as it cools, we can really start talking about what kind of energies that are in these colliders. Okay, so let's move to a blank page here. All right. Okay, so now that we've spent a great deal of time on the particle physics surrounding the early universe, I can really get into it, and I can really give you some idea about the history of what happened really in the first few minutes of the universe. And we say the first few minutes because we basically know what the size was, and we can sort of guess what the temperatures were. And if we guess at everything being in one little spot and then spreading out as it banged away, we could tell you sort of what the temperatures were and what the energies were. Okay, and temperature is going to scale like the energy. Okay, because remember, the temperature is really just a average of the energies of the different particles. Okay, and I'll give you guys energies and temperatures. The energies are going to be in those electron volts, and the temperatures will be in Kelvin. And the Kelvin scale is like the Celsius scale, but it's that plus 273 degrees. Okay, so it's just off by a little bit extra. Okay, and that 273, remember, is to get us back down to absolute zero. Okay, so the idea here is we'll start with the very, very first beginnings, and what I can't say is physics, or what I can say, sorry, is physics doesn't know about the time before, now this is going to seem ridiculous, right? The time before 10 to the negative 43 seconds. Okay, now put this in your mind, right? This is 1 over 10 with 43 zeros behind it. Okay, 10 with 43 zeros behind it. The 10th, 1 to the 10/43 of a second, okay, which is not very much time. But I can honestly say that we just don't know what's going on there. And this is the realm, again, of quantum gravity. And it's actually what my research on is, on quantum gravity. And there's not much that we can say about it, okay? And this time scale relates to about 10 to the negative 35th meters, okay? And this is called the Planck length. I can make up units if I use something called the Planck's constant, which is a constant from quantum mechanics. This 1 over 10 to the 43 is called the Planck time, okay? And physics can't tell us about what happened before the Planck time or anything smaller than the Planck length. And this is in general, really. This Planck length is in general. We can't tell you about physics below this length, okay? This might be where strings live, or for string theory, things like that. And we'll touch on those topics a little bit later. Okay, this corresponds to about 10 to the 19th GeV. Now remember, GeV is already 10 to the 9th EV. So that's like 10 to the 9 plus 19th EV. It's a big, big number. Okay, that's what kind of energies we're dealing with here. And so we just don't understand those things. So that's the very, very beginning. And I'm just going to tell you there's sort of a black box at the beginning. Now, the first part that I can talk a little bit about, which I'm not going to go into too much because the next chapter is all about inflation. But suffice it to say, from about 10 to the negative 43 to 10 to the negative 10 seconds, which is still 10 to the negative 10 seconds, is really small. The universe, now this is the real numbers, but it's not as impressive as I want it to be. The universe expands really, really fast. And it expands from smaller than a proton, okay, smaller than a proton, to, which is like 10 to the negative, so this is 10 to the negative 35 meters. Proton's like 10 to the negative 15 meters-ish. So smaller than that, smaller than a proton, to the size of a grapefruit. That's what your book says. I like that. Size of a grapefruit. Now, that seems like a grapefruit doesn't seem very big for the entire universe. But at some point it was. Remember, we're talking about the Big Bang here. And that fold difference is really, really fast. It's really fast. And we'll talk all about that next week. Okay? And this is what inflation is. And that has a lot to do with how homogeneous the universe becomes and things like that. And we'll talk about that later on. But the next step that I want to talk about, let's do some, so I can do some erasing here, is at 10 to the negative 10 seconds. This, what happens here is the electroweak force, which I haven't talked about the unification of these, and we'll talk about this a little bit at the end, and what I mean by electroweak. Okay, but this is where the electromagnetic force and the weak force are actually combined. They separate into their two respective forces, and this is about energies of 100 GeV. Okay, so already we're getting much smaller. Up until now, the universe is a soup, a hot soup, a really hot soup of all the particles, all the intermediate particles, all those intermediate bosons. So there's gluons and W and Z bosons and photons flying around and colliding in with each other and things like that. Okay, and at this point, the electroweak force separates out. And at the next level, as the universe expands, it gets cooler and cooler. That's the idea. So as universe expands, it cools. Okay, and so the next stage is called the Hadron era. Now, if you remember from before, I might have implied it before, the Hadron era. Sorry, hadrons are the three quark things, the things that are made up of three quarks, like protons and neutrons and other more exotic ones. This is at energies of about 1 GeV, which corresponds to about 10 to the 13 Kelvin, which is really, really hot. These temperatures, and this is at about 10 to the negative fourths of a second into the creation of the universe, the photons, okay, so what we believed was the universe, right, up until now was just those intermediate bosons, okay, and at this point the photons are going so fast, that they're coming in and they're actually creating now. Before, remember, I was writing electrons here, but here they're making protons and antiprotons, and they're also making neutrons, okay, and the photons are so big that they're making antiparticle pairs out of these guys, and this would be a antineutron, which I can draw with the bar over it, right? Antineutrons, and it's so big that they're making these huge, massive particles, and we start to see these, and it's still hot enough for this to be happening, and it has to do with how the forces are separating out and things like that, what we get at which different eras here. After the Hadron era, we have something called the Lepton era. Okay, that's why I've went over all these names before, because this is just what they're known as. And what happens here, we've got energies of about 100 MeV. It's about a factor of 10 below a GeV, talking about Kelvin, 10 to the 12th Kelvin. And here it's cooled down so that we don't get protons from photons, but the photons are still energetic enough to make the leptons. So we're getting neutrinos, and we're still getting electron-positron pairs here. And this is a very important region that lasts for about, the era lasts for about 5 seconds. We're not talking about geologic eras here. This is a very important era because these electrons and positrons now that are cool are, now again, remember, we don't have positrons and electrons, we don't have protons and antiprotons and neutrons until this Hadron era. Until then, until after the electroweak force separates out, we don't really get these things forming. Now that we have protons and electrons, we get neutrons, and because of the reaction, well, the opposite reaction of what I was talking about for neutron decay, you get positron plus an electron, giving you a neutron plus a neutrino, actually. And this is very important. We got the electrons and the protons around to give us this reaction, and this is where we get most of the neutrons that are formed. And the neutrons are a really important measure of how we get other nuclei. Now, the neutrons by themselves, again, as I said, neutrons decay in about 8 minutes. Your book says 10 minutes. It's a little more than 8 minutes. But they decay really rapidly when they're by themselves, unless they get put together with other protons. So if you put a neutron and a proton together, if you can put 2 neutrons and 2 protons together, you get a helium nucleus. And that's the second thing we're going to talk about. So this is the Lepton era. A lot of neutrons are formed in this era. Okay, and after this era, you get something called nucleosynthesis. Okay, and I want to talk about nucleosynthesis, but the first thing I want to talk about is something your book refers to as baryogenesis. It's Baryogenesis. Okay. Baryogenesis is sort of a misnomer. It really talks about the idea that there are particles. Remember, there are particles and antiparticles around. And remember, if the particles and antiparticles collide with each other, you get pure energy, right? So the fact that they're both around means that everything is in a state of flux, right? You get photons that are so energetic they produce protons and antiprotons, and then it cools, and then they produce electrons and positrons. But then those positrons and electrons find each other, boom, they form light again, and the protons and the antiprotons find each other, and boom, they form light again. And for some reason, the world is made up of only particles, not antiparticles. And so it turns out that there were a few more particles than antiparticles. And of course, they're called particles because they're the ones that we see all the time. If they were the other ones, they'd be called particles, and then we'd call the other ones antiparticles. Anyways, it turns out that about 1 in 30 million particles survived. So there were a lot more particles at one point in the world, and antiparticles, but they all collided with each other and formed a ton of photons again, and we're only left with 1 in 30 million of them left. Okay. And this is called baryogenesis. What it basically means is that we have all of these particles left over, and the baryo is really those heavy ones like the protons and the neutrons. And so that's what we're left with. Now, once we're in a stable state, once most of all the antiparticles are gone, we can actually go into the part of the creation of the universe where we get nucleosynthesis. Now, of course, the simplest nucleus is a proton surrounded by an electron, okay, flying around it, right? That's the idea. But then we can have bigger nuclei. You can actually have a proton with a neutron. You can have a proton with 2 neutrons. Okay? These are all still helium. This is helium. This is also helium. This is helium-1, helium-2, because it has 2 nucleons in it. This is helium-3. Okay? And then if I put in one more proton now, so I get helium proton, 2 neutrons, 2 protons. This is actually helium. Okay, and this is helium-4 because there's 4 nucleons in there. All right. And just so you know, and your book refers to this guy is deuterium. Deuterium means 2. Well, it's hydrogen with 2 nucleons. And this is tritium, which is a T. Tritium is hydrogen with 3 nucleons. Okay, and the idea is we start with these simplest nucleons, and we can kind of move up the chain. I'll show you how that happens here in a second, to get bigger and bigger nuclei. And it turns out we end up with things a little bit bigger than helium, and go up the table of the elements just a little bit further. But we can make these bigger nuclei, and there was a short time, just kind of after baryogenesis happens and the particles and antiparticles all annihilate each other, we're only left with a few particles, where you get these chains, and the chains really depend on the presence of neutrons as well. And the way the chain goes is neutron plus a proton, these are nuclear reactions, gives you a deuterium plus a gamma. Remember, gamma is just a photon of light. Okay, and then once I get a couple of these deuterium around, I can get 2 deuterium. That'll give me a tritium, and a proton, and again some more light. I also have a reaction where instead of getting tritium, I get helium-3, which helium-3 would be, let's draw helium-3 over here. Helium-3 would be 1 neutron, 2 protons. Okay, that's helium-3. It's 3 nucleons, but it has 2 protons, which makes it a helium. Sort of assuming knowledge about how these particles are made up over here. I maybe shouldn't, but the name of the element tells you how many protons it has, right? Because that's the chemical properties of it have to do with how many electrons and how many protons it has. So helium has 2 protons. The 3 means it has 3 nucleons. If it has 2 protons and 3 nucleons, the only thing that's left is a 1 neutron. That's the idea here. Helium-4, right? Helium-4 has 2 protons because it's helium, and it's a 4, so it has 4 altogether, so I can figure out that the other 2 are neutrons, kind of down the line. Okay, back to these just to make sure everybody's on the same page there. I can also get helium formed from 2 tritium that form a helium nucleus, and then 2 protons. I get 2 protons and, of course, more energy in the form of photons. Now, this is called a reaction chain, okay? And the reason is this is called a chain reaction. And the reason it's a chain reaction is because these protons up here can now go back in, any of these protons can go back in and make more of these things, and so can these neutrons as well. Okay, and so they feed on each other. In the end, you get neutrons and protons that allow you to make more and more. Now, of course, all of these things have to have certain amounts of energy to combine and hit each other the right way. But then we get helium. Now, the big thing that your book sort of neglects to tell you is that helium is a very stable nucleus. Very stable nucleus. And the fact that it's very stable means that once you get to helium, you have to work hard to get bigger. Okay, so we get beryllium and some other, so beryllium and lithium. Beryllium's actually bigger than lithium, but small amounts. We get really small amounts because it takes a lot to sort of get past the hump that helium is at because it's so stable. And once you're there, you kind of stay there. Okay, and then you're good to go. And those neutrons that decay really fast, once they're in a helium, they're stable and they're okay and they're happy. Okay, and this nucleosynthesis era lasts for only a very short time, and the environment had to be perfect. Okay, and actually, the Big Bang and the way the Big Bang cools in the right order, okay, has a lot to do with how we know how much helium there is. And we can actually figure out some of these time scales by figuring out what the percentage of helium is in the universe and things like that. And your book talks about that a little bit. Okay, let's see if I can erase this here. And so your book kind of makes a big deal about the helium abundance. And it's about 25% of all of the nuclei that are in the universe are helium, and this amount really does sort of imply the Big Bang and tells us something about how long we were in the different eras. And it has a lot to do with, again, that lepton era and the neutrino concentration. And you can read a little bit more about that in your book. But the neutrino concentration, there are other reactions that depend on having neutrinos around, and it still has to be warm enough for the neutrinos to interact. So once it cools to a certain point, neutrinos stop interacting. And this is before recombination from photons and things like that. And so what ends up happening is the neutrinos go free, and the universe becomes transparent to them at some point, and then you sort of stop getting those reactions. Okay. Then after this, just a little bit further along the way, we get recombination, which, again, recombination I'm not sure is the best word because nothing was necessarily ever combined, but then you actually start to get atoms. And the telltale sign of an atom, right, is electrons bind to the helium and the protons, so they bind to the nuclei. And then you get all those photons that are given off by those bindings, and this is where the CMB comes from. The cosmic microwave background radiation is when these photons all come off of those. And this is at about, now this takes a while, right? This is at about 380,000 years after the Big Bang, which comparatively isn't very long, but compared to all of these other eras is pretty long. And this is at about 3,000 Kelvin. And we know this, we can measure what temperature we need to get to strip all the electrons off of helium gas. Okay? And so, and we get all this stuff happening after that point. Now, let's have a little picture here. You know, here's that 10 to the negative 43 seconds. We don't know really what happens after there. And this is sort of the different eras of what's going on. Okay, and then at this 300,000 years, look at these years, right? We're talking about 10 to the negative 34, 10 to the negative 10, 1 second, 3 minutes. Okay, so after the first 3 minutes, we really have all of this. After this 3 minutes, we have helium abundance and hydrogen abundance and their relative abundances all figured out. And then we have 300,000 years till it cools down enough so that the photons are no longer bound. They're not colliding with things anymore, and we get the CMB coming off right around then. And then this next era, okay, we have atoms, but this next era is called, and your book refers to it as the Dark Ages. Okay, this has nothing to do with dark matter or dark energy. This is just the era where we don't have stars. So there's no stars yet, because we haven't had enough gravitational collapse to get everything to hot enough again to give us stars. Okay. And the last topic I want to talk about here is something called unification. And many of you may have heard of unification. I talked about it a little bit when I talked about the electromagnetic force. And you can read some more details really in your book here. But the idea is that, remember that electromagnetism was really a unification. Faraday figured out that they were the same thing. We thought that they were different. Well, it turns out that if it gets hotter, so I'm going to kind of draw an arrow here. This is hotter or bigger energy as I go down the pipe here. As I keep going down, what ends up happening is that if I look at the weak force and the E and M force, if I look at the theory behind the two, they actually combine into one force. Okay, so as I go hotter and hotter, they look like the same force. And it's not, the idea is that as they really, we should go backwards, and as they cool, they separate out. They look like two different forces. But as I go further back in time, they look like the same force. And if I consider the strong force in here as well, okay, if I consider the strong force in here as well, as I get even hotter, so way down here, it would look like all of these would look like the same force. Okay, it looks like the same force, and this is called a grand unified theory. Now, let me give you a little history here. We don't have a grand unified theory. Yet. But we do have something called an electroweak theory. And this is Weinberg and Salam. Got the Nobel Prize for predicting this. Basically, I can look at the math and the theory of the electromagnetic interaction and the weak force, and at some point I go way back in time, and those bosons that are in the weak force, I can get to a point where it looks like they don't have mass, or at least they have so much energy that it doesn't matter. They can move super close to the speed of light, and they look like the same force. E and M and the weak force look like the same force. everyone assumes that this will happen, that the strong force will come in here and interact. And we understand all of these guys on a particle basis pretty well. So we assume that there's a grand unified theory. And of course, if I go back far enough in time, if I go back way back to the beginning of the universe, there's an idea that there should be some theory here that is all the forces. Okay, and this is called a TOE, which is a theory of everything, which means a theory of all of the forces in one place, right? And that is TOE, TOE, which is a very not the best name for a theory of everything, I guess. And this is something that we don't see. This is supposed to happen at that 10 to the negative 43 seconds, way back in time, and we don't really know what this would be like. This would again be in the realm of quantum gravity. Okay, and the idea is that time, of course, goes this way, right? This is time, and as the Big Bang happens down here, this is the Big Bang. The forces separate out, and we say that somehow the symmetry is broken between them. What that means is the symmetry here means that all the forces look the same, all the particles look the same, and we can't tell the difference between them. Okay, and as stuff cools out, we start to see things happen. See gravity kind of come out. We say that it freezes out at like 10 to the 16th GeV or something, which is pretty crazy. But we see gravity kind of come out as a separate force. Then we start to see the strong force come out, and then we start to see the electroweak force break apart as well. And all of these stages have a lot to say with what era we're in for the early universe. Okay, so I hope that's a pretty good big picture about what happened. We'll touch base with some of those different parts of the eras, parts of the history again, and go ahead and read through your book. There's some more details in there, and thank you very much for your time.